Okay, I think that should do it. All right. So, we left off last Friday, having just defined the notion of cardinality of a set, which remember we said was some kind of measurement of the size of a set. Yes, and in the morning section we had stated a bunch of properties of cardinality. And we did not do that in the afternoon section. So I'm going to start by, well, we're going to prove all these properties. So I will just list them one by one and prove them as we go. Yeah. So we had a bunch of properties of cardinality. Line here to remind myself to divide the board in half. Okay, so in general, we have A and B sets. And then we said a bunch of things. Firstly, if A is finite, and B is a subset of A, then we also have that B is finite, where the cardinality of B is less than or equal to the cardinality of A. And furthermore, we have that these cardinalities are equal if and only if we have equality of sets. Yeah. Okay. So I guess I should point out here that of course, remember, in the case that we have a set with finite cardinality, this means that there exists a natural number n and a bijection from that set, say A, onto the set of the first positive natural numbers, 1 through n. And so this is what I mean when I say A, for example, is finite, that there exists such a natural number n and a bijection. Yeah. Okay, so how do we look at this for the proof? We will use induction on the cardinality of A. The base case tells us what? What is the base case? That the cardinality of A be what? Yeah. 0. Yeah. Good. And what did we say by convention? A set with cardinality 0 must be equal to the empty set, right? What is the only subset of the empty set? Remember, the empty set is defined as the set with no elements, right? And in order for some other set to be a subset, we need to have every element of B is also an element of A. So the only subset of the empty set is again the empty set. Yeah. So B is subset of A implies that B is also the empty set. And so the cardinality of B is also equal to 0, which is less than or equal to the cardinality of A. Yeah. Note here, we also have that as we said in our additional part of this claim, that we must necessarily have equality of sets here. Yeah. Sorry, let me just make sure. Yeah, that I'm aware if anybody asks a question over Zoom. Yeah, for those of you who are in the Zoom call, if you have a question, just type it in the chat and I'll remember to check regularly. Yeah. Okay, good. So in this case, our induction hypothesis says the following. We assume the proposition true for the cardinality of A is equal to K. For K greater than or equal to 1. Then we'll show the inductive step. For the cardinality of A into K plus 1, if D is equal to A, then the result is trivial. Just by our definition of equality of sets, this means that there has to be the same elements as there are in B as there are in A, right? So we get this automatically. Okay, so we will assume B a subset of A with B not equal to A. Okay, so since we have the cardinality of A is equal to K plus 1, there is a bijection F, which goes from A onto the collection of the first K plus 1 non-negative, or sorry, positive natural numbers. Then the set F of B, which is the collection of elements I in the set, the codomain of F, such that there exists X in A with F of X equal to I. Sorry, X in B. Yeah, the collection of elements that get hit in the codomain by taking input values in the set B. Yeah, this is called, you may recall, this is the image of B under the set F. Yeah. Okay. Um, so this set is a proper subset of the codomain of F. Yeah. Um, since F is a bijection, and B is not equal to A. Yeah. Okay. Then we may form a new function. F restricted to the domain B denoted by F vertical bar B that goes from B onto um, F of B. Okay, that is to say, all I'm doing here, this is notation for I will now restrict the potential inputs into F just to the subset of A, the domain of F, B. Yeah. Okay. Um, this function F restricted to B is a bijection. This is a bijection which uh, shows that um, the cardinality of B is equal to L for some L strictly less than K plus 1. And then we can simply relate the elements of F of B as 1, 2, up through L. That is to say, e.g., let's say F of B was equal to oh, I don't know, let's say 2, 3, up through k minus 1, sorry, k plus 1 minus L plus 1. Then I can just create a new bijection where I'll just send 2 to 1, 3 to 1, and this to F. Yeah. We'll call this, say, G. Okay. Then what we have is G composed with F restricted to D is a bijection from B to the first L positive natural numbers. Yeah. Which tells us that the cardinality of B is equal to L, which is strictly less than k plus 1, the cardinality of A, which is what we wanted to show. Part 2 of this proposition. If A and B both finite, then the cardinality of the union of A and B, let me put this on the next line, is equal to the cardinality of A plus the cardinality of B minus the cardinality of the intersection of A and B. In particular, if A and B are disjoint, then we just get the cardinality of A union B is equal to the sum of the cardinalities of A and B. Yeah. Okay. So we'll actually prove the second part first. Let us first assume that A and B are disjoint. Okay. And we will also assume the cardinality of A is equal to n, and the cardinality of B is equal to m. Okay. So there exist bijections f going from A to 1 through n, and g going from B one through m. Okay. Good. Then the function h, which I will say goes from the set 1 through n plus m onto the union A union B, defined by h of k is equal to um, f inverse of k for um, k from 1 to n, and g inverse of k minus m, k minus n, uh, for k between n plus 1 and n plus m. Okay, so what am I using here? Recall a function is bijective. If and only if it has an inverse function. We proved this when we first described what it meant to be a bijection, namely that we are both injective and surjective. And then we showed that these are exactly the functions for which an inverse function exists. Yeah. Okay. So what I'm saying here is that since f and g are both bijections, I can come up with an inverse function for each of them. Yeah. And I will define this new function h that takes the set of the first n plus m non-zero natural numbers onto this union. Yeah. Okay. So what do I want to say from here? I want to say then h must also be a bijection. What do I need to verify that H is a bijection? That it is both injective and surjective, right? Well, surjectivity is pretty easy, yeah, because every element of A corresponds to one of the natural numbers between 1 and n. Yeah. So I know that every element of A will get hit by just one of these values here. As for any element of B, which cannot be an element of A also, right? Because we assumed first that A and B are disjoint, then, well, what I mean to say here is that every element of B I can associate to one of the numbers, the natural numbers, 1 through m. Yeah. Then just by the definition of this part of H, I know that I have to hit every element of B. Injectivity is maybe slightly more work, but also not so hard if you just sit down and write down the definition of inject. Yeah. Okay. Therefore, well, because H is a bijection, that means H has to have an inverse function, right? Which is also a bijection. H inverse, which goes from the set, sorry, A union B onto the set 1, 2, up through n plus m, is also a bijection. So the cardinality of the union A and B is equal to n plus m, which is just the cardinality of A plus the cardinality of B. Yeah. Okay. In general, uh, note that A set minus B um, and A intersect B are both finite. Why? Why do I say that both of these sets are finite? Yeah. Yeah. These are both subsets of A, right? So by one, if I assume that A is finite and I have some subsets of a finite set, I must also be finite. Yeah. So let's write that down. Since A set minus B and A intersect B are both subsets of A, which is fine. Okay. So then Uh, Also note that A set minus B intersect A intersect B are disjoint. You can write this symbolically. Yeah, just by the definition of the set difference and intersection, right? Here's just not a proof, but a schematic diagram, a Venn diagram. Here's A, here's B, then here's shaded A set minus B, and then shaded the other way is A intersect B. Yeah, these are destroyed. And we also have the union of these two sets is equal to all of A. Yeah. Therefore, the cardinality of A, which is equal to the cardinality of A set minus B union A intersect B, is equal to, because these sets are disjoint, this, right? By the first thing that we proved in part 2. Okay. So what does this tell us? What do we get from this? B. Um, so this is equal to the cardinality of, well, actually, let me be a little more explicit here. I will rearrange slightly here. Which is the cardinality of A set minus B. No.
We want to break up B also and realize there's two copy of the intersections later.
Oh, okay. Yeah, so let me start again here, right? So that is to say B is also equal to B set minus A union um, A intersect B, right? So, which implies that the cardinality of A union B is equal to the cardinality of A set minus B union A intersect B union B set minus A union A intersect B. Yeah. Okay, so same A set minus B union B set minus A. If I take the union of this twice, then I just get A intersect B, right? Okay. So then, check on this here. Um,
And then since that we are just sure we can break it up.
yeah, definitely. Being able to do this for 3 sets, right? But this, and this are all disjoint, right? So that is to say, for example, I can have cardinality of A set minus B plus the cardinality of B set minus A union A intersect B. You have this, yeah. So then uh, oh, I'm sorry. I feel like I'm missing a step here.
And you can just unwrap the other side equation, A equal to that under the right corner and B the same, so that two copies of the English like we do that. It's fine.
You're saying
Thanks. And so you have this on the left side, and then the right side, you have cardinality of A can be bringing up to the top right part. The two is joint.
oh, you're saying that this should be
No, just the cardinality of A plus the cardinality of B kind of breaking it into four parts.
hmm, can be equal to the cardinality of uh this, yeah. Which again, because these are this and this are disjoint, this and this are disjoint, I get the cardinality of A minus B plus the cardinality of A intersect B plus, like I said, I'll leave these parentheses, plus the cardinality of B minus A plus the cardinality of A intersect B. Yeah. So now combining these, we have the cardinality of A union B is equal to cardinality of A plus the cardinality of B minus one of the copies of the cardinality of A intersect B. Yeah, good, thank you. Okay. Good. So, thirdly, uh, A is finite. And the any set, then we have the cardinality of A set minus B is equal to the cardinality of A minus the cardinality of the intersection of A and B. Okay. Again, by one, both A set minus B and A intersect B are finite. Since they are disjoint, we have the cardinality of A equal to the cardinality of A set minus B union A intersect B is equal to the cardinality of A set minus B plus the cardinality of A intersect B, which implies that the cardinality of A set minus B is equal to the cardinality of A minus the cardinality of A intersect B. Okay, you can actually use this as an easier way to prove two.
You actually just wrote it on top there.
Yeah, I just said that this is the case, right? So perhaps I did this in kind of a backwards order, but we got there eventually. Okay. So so fourthly, A and B are now finite. Then the cardinality of the Cartesian product of A and B is equal to the products of the cardinality of A and the cardinality of B. Okay. So we'll take the cardinality of A to be N and of B to be M. And we'll take the explicit bijections F going from A to natural numbers 1 through N, and G going from B to natural numbers 1 through M. Okay. Then we will define function H going from natural numbers 1 through the product n times n to A cross B by the formula H of A plus n times B minus 1 is equal to f of A, comma, sorry, f inverse of A, comma, G inverse of B. So what am I saying here? I guess I should be slightly more specific here. For A between 1 and N, and B between 1 and M. Yeah. Okay. So this is a bijection. And so H inverse goes from the Cartesian product of A and B onto this set of natural numbers 1 through N times M. So the cardinality of A cross B is N times M, which is the cardinality of A times the cardinality of B. Now, you might be asking yourself, it's like, well, why did I define the bijection going from the set onto this, where I have to do all this inverting? It's just a choice, right? One way or the other. You'll have to do some inverting to prove some of these things. So the point is that whenever we have a bijection, we can come up with a function that is the inverse function, which is also a bijection, which again is what we proved way back when we first defined injective, subjective, and bijection. Okay. 5A is infinite. And A is a subset of B. Then B is also infinite. In particular, A union C um, is infinite. Exactly when one of A or C or both are infinite, right? That is to say, if you look at the union of A and C, remember that will always have a subsets A and C. Yeah. Okay. So proof. Supposing A is a subset of B, but one if B is finite. Then A must be finite. Okay. So considering the contrapositive, gives A infinite, implies B infinite. Secondly, if A or C infinite, we know that it's always the case for any union that the things that you're unioning together will both be subsets of the union. Okay. 6. A is infinite. And B non-empty. Then we must have A cross B infinite. Note, uh, we must have this equation for a Cartesian product with an empty set. So the hypothesis that V is not the empty set is necessary. For this result. Yeah. Well, all right. Prove this now. Supposing that A is infinite, um, let X be any element of V, which we can find since V is non-empty, right? I know that I can find some element X of V. Um, then the set A Cartesian product with the single element set X is a subset of A cross B. This goes back to the properties of Cartesian product that we discussed also quite a while ago. Now, okay. Come in if you want. Sure. Okay. So what does this tell us? also, there is a bijection. Let's say capital F that goes from A across the single element set X into A, given by F of the ordered pair A comma X is equal to A. What's the easiest way to show this? F inverse. It goes from A to this set defined by F inverse of A is equal to the ordered pair A comma X in an inverse function. Yeah. That is to say, if I compose F and F inverse and F inverse and F, I'll get the identity function on both sides. Therefore, A cross the single element set X is also infinite. Right? That is to say, it is in bijection with the infinite set A. So it must also be infinite. Okay. Then by part 5. Find A cross B is infinite. Okay. Couple more properties. F is injective. Then the cardinality of A is equal to the cardinality of the image of F. Oh, sorry, I guess I should say F to tell you what the domain and codomain are. F going from A to B injected, then I have the cardinality of A is equal to the cardinality of the image of A. What again was the image? Where the image of A, another way to write this is F of the set A, right? This is the collection of all elements B and B such that there exists an A and A with F of little a equal to B. It's just the set of all elements of the codomain that are actually realized when we take all values of the function. Yeah. Okay. Proof. The function F gives a bijection between A and the image of F. That is to say, we're shrinking the codomain to the collection of values of F that are realized, which implies that we're making it surjective. Okay, think about what I'm saying here for a second. If I start with F being injective, then if I shrink the codomain down to just the set of values that are actually realized as values of F, I'm not going to stop being injective, right? But by making the codomain smaller, I'm cutting out all the elements of V that are not hit by F. Here's a picture. So here's a set A and a set B. Let's say I have a bunch of points here in A and a bunch more points here in B. And what I'm saying here is that my function F will do something like this. We'll take every element of the domain to some other element of the codomain. Okay, so all these red arrows are F. Then there's a bunch of elements of V that don't get hit, right? So this is injective, just by virtue of how I've drawn it, right? There's no two elements of the domain that get mapped to the same element of the codomain. So what I'm saying is I can take this subset this shaded subset is the image of F, yeah? And by excluding all the points in B that don't have corresponding values back in A, I get a bijection, yeah? Okay. So, since bijections preserve cardinality, we must have um, the cardinality of A is equal to the cardinality of the image of F. Yeah. Okay. So finally, if again, A and B are finite sets, with the cardinality of A equal to the cardinality of B, then a function f going from A to B is objective if and only if f is surjective if and only if f is bijective. Now, for those of you in the morning section, I wrote this down on Friday, but I forgot to put this hypothesis in that the cardinalities of A and B are equal. Yeah. If this is not the case, then certainly I can have a function which is injective but not surjective, for example. Yeah. Okay, so this is necessary for this proposition. Okay. So, for the proof, let us suppose f going from A to B injective. And the cardinality of A equal to the cardinality of B. Then by 7, we know F induces a bijection from A to the image of F, right? We have, this is just the statement of our last piece of our proposition. So the cardinality of image of F is equal to the cardinality of A, which by hypothesis is equal to the cardinality of B. But then, since B is finite, and the image of F is always a subset of V, right? Look back at this schematic picture, right? The image of F is just the values in the codomain that actually get hit by the function, right? So this will always be a subset of the codomain. Yeah. So we have two finite sets, the image of F and B, which have equal cardinalities. What does that tell us? That the sets themselves have to be equal. Yeah. Which is another way of saying that F is surjective. Yeah. So, which again implies F is bijective. Right? Because we started with the assumption that F was injective. Okay. So conversely, what can we say? Conversely, let's suppose f going from A to B is surjective. Um, and then let us define S sub A, oh sorry, S sub B, call it, the set of elements A and A such that f of A is equal to B. Which I know is non-empty for all B in B. What is the point of defining this set? Well, I'm ultimately trying to show that F is injective, right? So that is to say, I want to show that S sub B, the set of all elements of A that map to B, has one element for each B in B. Yeah, there's not more than one element of the domain that maps to the same element of the codomain. Yeah. Okay. Then the collection of all sets of this form are disjoint. That is to say, for any B and B prime in B, B not equal to B prime, we have S sub B intersect F sub B prime is equal to the empty set. By the way, why do I say that this is non-empty for all B, little b and B? Yeah. Yeah, because it's subjective, right? I know that there's at least one element of A that maps to any B. Yeah. Okay. So why do I say that these are disjoint for any two sets? If X is in this intersection, then B is equal to f of X is equal to B prime, which is impossible since f is a function. Right? If I take two elements of B, B and B prime that are not equal, I can't have two outputs for any one input. Yeah. So that is to say, each of these S sub B's is non-empty. And if I take the intersection of any two S sub B's, B and B prime, not equal, I'll get the empty set. Yeah. Um, then we also have that A is equal to the union over all elements little b and b of S of B. Why is this? Since any A in A lies in S sub F of A. What is the conclusion of the last three things that I said? I have a collection of non-empty subsets of A, which are pairwise disjoint, whose union is all of A. What does that mean? Altogether, this means the S of B's form a partition of A, right? Take any two that are not equal, they're disjoint. None of them are empty. And when I take their union altogether, I get A. So I get a partition of A. Okay. And we also have that the cardinality B is greater than or equal to 1 for all B and B. Now, we said this already, but not in terms of cardinality, right? This is just saying that none of these sets S sub B are empty. Okay. And by repeatedly applying part 2, we have the cardinality of A is equal to the cardinality of S sub B1 plus the cardinality of S sub B2 plus the cardinality of S sub Bn, say, where the cardinality of B is equal to n. Right, so there's n elements in B altogether, and I just take each of the sets that are elements of my partition, and they're pairwise disjoint, so that means I will get this sum of cardinalities, is the cardinality of A. Okay. We must also have that the cardinality of B is less than or equal to this sum. Why is this? Yeah,
Each of the letters on the grid is at least one. So,
yeah, right. Since S of B is at least one for all B in B, right? And I have one of these sets for each element of B, right? So I have at least n ones on the right. But I also have that the cardinality of A is equal to the cardinality of B. That's what I said in the first place, right? That was my original hypothesis. Okay. Um, Meaning we have equality. Huh? The only way this can happen is if the cardinality of S of B is equal to 1 for all B and B. Yeah? Which is the same as saying F is injected. Which is just what we wanted to show. Well, I guess I should say slightly more, right? We started by assuming that F was surjective and then deduced that it was injective. So it's bijective. So this completes the proof of the final property that we wrote down. Okay, good. I think we've done enough for the day. I will post the lecture on YouTube and then send a link out via Canvas, just so you can look at it again, and for all the people that weren't here tonight. Yeah, good. Enjoy the holiday tomorrow, and I'll see you all on Friday.